This is Mr. Beck Does Your Homework. This is the entire homework, and I'm just going to give you some hints on each problem. This first problem is asking for the moment of inertia of a sphere that's rotating about an axis here. So it's spinning around as a sphere, but it's spinning around up by its edge. How about you treat this as extra credit and Google it? So the answer here is Google. See if you can figure it out. If you can't figure it out from Google, then look up something called the parallel access theorem. It's pretty neat because it makes this a very easy problem. But you'll have to use either Google for a sphere rotating around its edge or the parallel access theorem. And either one of those will give you a bonus set of points on this one. Okay. Here we've got a guy who is zipping around because of this rocket. Now this 300 meters per second, or whatever your velocity is, that is the velocity of the gas escaping the rocket. So really we have a mass concentrated on the edge of a circle. So the moment of inertia of this guy is just his mass. For me it's 240 kilograms, and it's going to be mr squared because all the mass is on the outside of the circle. So when it asks for the moment of inertia of the rider, box, and rocket about the pole, that's going to be mr squared. The rocket develops a thrust perpendicular to the path of the rider. What's the angular acceleration? Well, that many newtons, it's going to give me a torque. And if I want my acceleration, I know that just like F equals ma, I know that torque equals I alpha. So you're looking for alpha here, and you know the moment of inertia from the previous problem, and they give you the torque, and the torque is going to be actually Rf. So you know the force that it is pushing with, which is 75 newtons. That's my force, and the radius, of course, is for me 4 meters. So you've got Rf, and you know I, and you're looking for alpha. Next, it says after what time is the rider's velocity equal to 10 meters per second? It helps to know some equations of motion. So by this time you know alpha, you know that your initial velocity is going to be 0. You're looking for where your final velocity is what was given. For me it's 10 meters per second. Actually, meters per second would not be omega, it would be a velocity. So it's 10 meters per second is my velocity, but if I take that and divide by radius, then I get my final omega. And after what time? So you're looking for the time. So you need an equation with omega 0, omega, alpha, and t. And I believe that is just that your acceleration is your change in your velocity, your angular velocity over time. So solve for time. Next problem. A fishing reel has a mass of 1.01 kilograms. Okay, this problem is dealing with a fishing reel that is going to be acting as a solid cylinder of a radius r. What's happening is that the fish is pulling out this way with a certain force, and there's also a frictional force of some sort that's pushing the other direction, also at that radius. So I've got a torque because of this force at this radius that's pulling out. I've got a torque because of this force at this radius that's pulling in the opposite direction, and I'm searching for the force of the fish. Now what I know is that the net torque is going to be the moment of inertia times the acceleration. So that's like F equals ma. So the moment of inertia is easy to figure out because it will be, it's a cylinder, a disk, so it's going to be 1/2 mr squared. So I'm going to get a 1/2 mr squared. And then the alpha, they give me the angular acceleration here of 50.7 radians per second. So that's my alpha. And my net torque is going to be the difference of the fish pulling. So that's going to be an Rf minus the Rf of the restraining torque. But they already give you what the whole restraining torque is. So this is 1.42 for me, is the whole Rf here. So I know this R, I know I'm looking for the force. This Rf is given to me. I know the mass and I know the radius. So I can use all of this and solve for the unknown force of the fish. The next question says, how much line unwinds in this amount of time? Well, now I can figure out, I know my alpha, I know my initial omega is 0. I'm looking for the amount of line, so I'm actually looking for an x. But if I can solve for theta, then I can use theta times r is going to give me x, or x divided by r giving me theta. I want centimeters. And then I know that my initial velocity is 0, and it gives me the amount of time, so I know time. So I've got alpha, omega, x, and t, actually alpha, omega, theta, and t, and I know that theta is going to be my initial velocity times time, but that's 0, plus 1/2 of my acceleration times time squared. So you can either you can either use your actual alpha and solve for omega, and then multiply by r to get x, or you can take your alpha and multiply your alpha by r to get your actual acceleration, and then just solve for an x over here. So one way or another you're using this, but the key to this problem is knowing that there are two torques acting in opposite directions, one clockwise, one counterclockwise, and it's the difference between them that's causing the cylinder to rotate. Question 7. Question 7 is pretty straightforward. I thought this was actually an earlier question. But for question 7, what you have is you have this rod that is going to be pivoting around this end, and you have a force of gravity that's acting right here in the center. And the angle that that's acting at is you need a theta, because your torque is going to be RF sine theta. But theta is the angle between the radius and the force. In this case, the radius is this way and the force is this way. So the angle you're looking for is this angle, which is going to be 90 minus this angle. So for me, it's 90 minus 29 will give me my theta. So there's my theta. My force is going to be the force of gravity, and the r is going to be this half the rod. So I've got RF sine theta. Now I'm looking for my acceleration. Well, that's my torque. And I know that just like F equals ma, torque equals I alpha. And you're looking for alpha, so now you just need the I of a rod, and they tell you that the moment of inertia is 1/3 ml squared. So that'll allow you to plug that in with the full length here as your L. So you should be able to handle that. Next question, questions 8 and 9. Here again, just like the fishing reel, I have a potter's wheel of radius 0.32 meters. So let me draw that really quickly. It's moving, freely rotating at 72 revolutions per minute. So I have my initial omega. And the potter can stop the wheel by pressing a wet rag against the rim. So what he's going to be doing is, if it's spinning counterclockwise, then he's going to be applying a clockwise force, which is going to be his force applied at some radius to give me a torque. Now we're actually going to be solving for the torque in here in part 2, so we don't even actually need the force and the radius itself. We're just going to need the torque. So we'll solve for that in part 2 here. But part 1, it gives me several variables. It gives me my initial omega of 72 for me, so I've got my initial omega. It tells me that he can stop it in 2.3 seconds, so stop it tells me that my final omega is going to be 0. And my time is 2.3 seconds, and I'm looking for alpha. So here, my alpha is going to be my change in velocity. So omega minus omega 0 divided by time. So that's pretty straightforward for my alpha. Now part 2 says that I'm looking for my torque, and I know from before that just like F equals ma, my torque equals I alpha. So you need the I of the potter's wheel, which is going to be 1/2 mr squared alpha, and you're going to be solving for the torque. So that should be not too bad. Solve for the torque there, 1/2 mr squared alpha. Moving on to our next problem, we find a bicycle tire of radius 0.31 meters, and mass 1.2 kilograms is rotating at 78.3 radians per second. So that's my initial omega. What torque is necessary to stop the tire in 1.3 seconds? So the time is going to be, for me, 1.3 seconds. And I know that my final omega is going to be 0, and I'm looking for the torque. Well, I don't have any equation that just gives me torque, but if I can solve for my alpha, then I can do torque equals I alpha. So just like F equals ma, torque equals I alpha. So I can solve for that. Now how do I get my alpha? Well, I know my initial velocity, I know my final velocity, I know my time and my alpha. So my acceleration is my change in angular velocity divided by time. Once you get your alpha, then your torque equals I alpha. And of course I, for a bicycle tire, all the mass is going to be on the outside of the bicycle tire. I think that's the hint when you're thinking about a tire. So my moment of inertia for a bicycle tire is going to be simply mr squared. That's going to be my moment of inertia for the tire. So I think you have enough information to solve question number 10. Question number 11 says a 16 kilogram solid cylinder has a radius of 0.313. If the cylinder accelerates at this rate as it rotates, how large is the torque? Well, this is even simpler than the previous ones, so they're kind of in reverse order. But here your torque is going to be your moment of inertia times the acceleration. You know your acceleration from this. You know that you're looking for the torque, and your moment of inertia for a solid cylinder is going to be 1/2 mr squared. So that's enough to solve question 11. And now the final question, question 12, this is the tricky one. A bicycle wheel has a diameter of 34.3 centimeters. So I've got a bicycle wheel. First of all, they're giving me the diameter, so you're going to have to cut it in half to get the radius. And it's got a mass. It's placed on a stationary stand on rollers, and a resistive force of 137 newtons is applied to the rim of the tire. So it's got a force this way of 137 newtons for me. And all the mass is concentrated on the outside radius. In order to give the wheel the acceleration, what force must be applied to a chain passing over a sprocket with a diameter of 12.4? Well, here I've got a second thing that I've got to worry about, and I've got a sprocket that's going to be located right here with a different radius. And again, they give you the diameter. So I've got a rope that's going to be pulling here with a certain force that's going to be trying to accelerate the wheel in this direction, and yet I've got a resistive force here that's trying to decelerate. So this is an example where your net torque is going to be your moment of inertia times your alpha. They give you the alpha, so that's good. Your I is going to be a bicycle wheel, so all the mass is on the outside, so that becomes mr squared. So you've got mr squared alpha on this side. But the net torque is the tricky part here. So what does mr squared alpha equal? Well, I'm going to put net torque on the other side just to make it easy to write. The net torque is the difference between the positive torque, which is going to be the force that's applying on the sprocket, and I'm asking, actually, what force must be applied to the chain. So that's the force I'm looking for, times the smaller r, which will be the radius of the sprocket. So there's RF for the torque, RF, minus the RF of the bicycle wheel. And so that's going to be the full radius of the wheel times the force that is the restraining force. So this restraining force of 137 newtons for me is going to be this force. This radius is the full radius of the bicycle wheel, which is half the diameter. This radius is the radius of the sprocket, and this force is the force you're looking for. So you know mr squared alpha equals the net torque, because the net torque, just like the net force would accelerate a mass, the net torque is going to accelerate the moment of inertia. I think you have enough to solve that one. And that's it. So good luck with this homework.